is it the case that the empty set is a vector space? This vector space. And you can get tricked because the first thing you say is, well, of course it's not. It's the empty set. How could it be a vector space? But then you think about it a little bit longer and you say, well, maybe it is because it's true. What does it mean to be commutative? Commutative means that for all u and v in V, u plus v is equal to v plus u. Is that a true statement about the empty set? Well, yes, because there's no elements to break it. So of course, the empty set has a commutative property on its elements because there are no elements. On the other hand, the property of additive identity says there exists zero in V such that, and then it does not even matter what comes after that, because I have asserted there exists a zero in V. Does there exist a zero in V? No, there's nothing in V at all, right? So this has to be false. There's no elements that could possibly be the zero in the empty set. So it can't be a vector space because it doesn't have any elements to be zero. In fact, one of the things that we're gonna show is that the smallest possible vector space is a set that has one element in it, and that element happens to be zero. It's not a very interesting vector space, but this is a vector space. Usually a homework exercise to prove that this is a vector space. I mean, is it commutative? I don't know. Is 0 plus 0, like I'm secretly going to switch the order of the zero. See, this 0 went over here. Those equal to each other? Well, yeah, right? 0 plus 0, 0 plus. Oh, look, so addition is commutative. For every element in the set, u plus v is equal to v plus u. So this is a vector space, but that isn't. Yep.
So for the identity additive inverse, the statement was, I remember, like for all v and v, there exists a w in v such that v plus w is zero.
That statement is actually true about this space because it says for all v in V, some condition must hold. Is there any v in here for that condition to apply to?
No.
No, so it's a true statement.
So we can say like W does not exist in that set as well, even though.
No, it's just that statement doesn't even apply. This is the weirdness of this kind of quantifier logic is you're saying what the statement about additive identity says. The statement about identity says for all V in, or additive inverse, says for all V in V, there exists a W in V such that V plus W is equal to zero. Okay, if you're going to tell me that statement is false, you need to find me a V that doesn't have an additive inverse. So where is the V that's inside that set that doesn't have an additive? Well, there is none because there's nothing in it. So this is a true statement, but it's true. The statement that gets used here is vacuously true. It's true because there's nothing to apply it to.
Okay.
So that's a thing that's in this sort of formal logical systems. If you have a statement that does not ever attain, it's just true, vacuously, because it can't be falsified because there's nothing to plug in. Okay. Yep.
I think that answers my question, but I want to clarify for a given element of vector space is the additive inverse also.
Has to be. Yeah, that's the deal. So, I mean, the axiom says that like, so the axiom says there must be an additive inverse in the same space. That's the first thing it says. And that's actually, for example, why are the natural numbers not a vector space, right? The positive integers. Well, the positive integers aren't a vector space because none of them they have additive inverses if you think about them as real numbers, but they don't have an additive inverse if you just think about the space as itself, right? If I say n is equal to 1, 2, 3, dot, 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 and I say, okay, this satisfies a lot of the rules of vector spaces. Mathematics, you know, the addition is commutative, the distributive property holds, associativity holds, but if you write an element down here and you want to cancel it out into 0, first 0 is not in the space. So it can't be a vector space. So you fix it and say, okay, well, maybe we'll use the other way that some mathematicians think about the natural numbers, where you just put 0 in. Oh, we'll fix it by sticking 0 into the set. Well, now there's a 0 in there, so we've got an additive identity. But it's still the case that if I wrote down 2 and I try to cancel it into 0, this doesn't belong to that set, so it can't be a vector space. Because the element and its inverse must both be in the space for it to be a vector space.
What about the case for the set is 0?
Okay, so, all right, so I want you to tell me, so what the statement says is, for every element of a vector space, it must have an additive identity. So I'm going to check every possible case. All right, there, I picked the element of the vector space. Now I have to figure out the element that I can add to it to get 0 out. Oh, okay. That's it, you did it. You checked all of them. Every single element, all one of the elements in here has an additive inverse, which happens to be itself. But every element has an additive inverse that's in the same space. And so that's closure. That's like
So the additive inverse can-
only when it's 0. Right? That's actually a feature of the 0 element, is that its own additive inverse. Yep.
Can I ask the same questions? Because I think what's triggering me is the sentence itself. Like, what if you rewrite that sentence as, for all V and B, there exists a 0 in B such that. So I feel like,
that, but it's not written that way on purpose, right?
so
You don't, there's no universal quantifier in the identity statement. It's an assertion of existence. These are axioms that are chosen to support the correct kind of mathematics. So this was a deliberate decision made in the construction of the rules of a vector space, that if there's not a 0 element, it's not a vector space. Just flat out. It's a binary choice. Mathematicians, when they were building this system, said, I don't know, should there be a 0? And then you do a bunch of math and you realize that in order for algebra to work, you better have a 0 element, or it's not even worth thinking about something as a vector space. So the reason there's no for all in here is to make this guaranteed to be inside a vector space. I mean, there's no other way to do it. Like at the bottom of the set of if you want to think about the category, oh God, I'm going to talk about category here for a second. If you want to think about the category of vector spaces, the thing that lives at the bottom is the vector space with one element. There's nothing smaller. Yep. Oh, that is a good question. So that comes from context. So for the additive identity, 0 is always a vector, because it doesn't make any sense to add a vector to it doesn't make any sense to add a vector to a scalar. So you can think about 0 as ultimately going to be represented by a list at some point, the coordinate list. Any other questions like that? Good? Yep.
So a scalar in our terms always must exist.
Yes. Yeah, a scalar. So when we say scalar, really we're thinking about I mean, the more abstract way of thinking about scalars is they act as a scalar field, which just means that they follow a scalar multiplication. But we in this class are going to think F, and F is always either R or C. And if you want to take that, I mean, after this class, these can be way weirder than this. But for us at the beginning, just R or C is enough, I think. Anything else? Okay, so I'm going to start with a bit of notation that Axler introduces as another example of vector spaces, but one that looks really weird on the page if you haven't been told about it. So this is his example 1.2.3 of an object that's a vector space. So it's an abstract looking thing. And he says that if S is any set, he's going to define this object, F raised to the S. And what he means by that is the set of all functions from S to F. So remember, a function is just a rule that takes an input in S and spits out an output in F, where each input only gets one output, right? So for example, if he writes this symbol, he means the set of functions from the interval 0, 1 into the real numbers. That's what he means. Every f that that starts with inputs in 0, 1, it spits out values in R. So to be an element of this set, you would have to look like it's an odd notation. Yep. Oh yeah, you absolutely could. He's not going to do that because he wants the outputs to be field valued, but you absolutely could use this notation to think about sets where you restrict the domain or the range as well. Okay, now one thing that you should be careful of when you see something like this is to not imagine that these things are all polynomials, because or continuous functions. In fact, almost every function in here is going to be some sort of horrendously nowhere continuous monstrosity, right? This is a really bad set. It's huge and terrible. But what lives inside of it are things like the continuous functions from 0, 1 to R live inside this space. And the differentiable functions and the integrable functions all live in here. Okay. But this is gnarly. All right. So I'm going to tell you that like the deal of FS, and the reason we introduce it is because anything of that form FS is a vector space. With the operations, well, I can combine two functions. So if I have f and g contained in this weird set, then the way I add them together is I just do f of x plus g of x. And if I have lambda in the field, and I have f, this weird space of functions, then lambda f, I'm using lambda because he does. For some reason, he decides to use lambda instead of c, just in this particular example. But basically, regular old functional addition and functional scalar multiplication. With those operations, this is a vector space. And one of the nice things about it is that we're going to see later on today is that if I know a big set is a vector space, if I can prove that smaller subsets follow the vector space rules, they're automatically vector spaces also. So this is supposed to sort of encapsulate all kinds of nice vector spaces, like the continuous functions and the differentiable functions. Okay, I have one more example of a vector space that I want to show you later that connects this up to algebra, but I'm not going to do it quite yet. I want to clean up the end. I'm not going to prove these, but I want to clean up the last properties that we had at the end of section 1b, just so that we have them available. So we had proposition 1.29. I'm sorry about the book edition thing. I downloaded it from SpringerLink and it gave me second edition instead of third. So my bad. I updated that online. Okay, so first off, 0 times v is 0 for all v in v 1.30. A times 0 is equal to 0 for all a in f. Axler goes out of his way to remind you, and I'm going out of my way to remind you, that that's the scalar 0 multiplied by a vector. This is the vector 0 being multiplied by a scalar a. This 0 is the 0 vector. That is a scalar a. That's the scalar 0 times a vector v. Okay. You have to interpret it this way because what you want to be true here is that this is the 0 vector. Okay, vectors don't magically turn into scalars. We haven't dot products yet, if ever. And then finally, my favorite fact, one that I might prove just because it's so amusing, but maybe not, is the fact that minus v, remember, minus v stands for the additive inverse of an element, right? Minus v is the additive inverse of v. Well, it turns out to be the case that minus v is equal to minus 1 times v. This is a name. This is a name for the additive inverse of v. This is actually bona fide scalar multiplication by -1. So the additive inverse of an element is just -1 times the original element, which is nice. Doesn't have to be the case if that's true. So this seems like a triviality, but this has a cute proof.
And this is the additive in
Additive inverse of v. And that sort of cleans up the last of our algebra. So you should read these proofs because especially the exercises in 1A, I think rely on this kind of algebraic manipulation that happens here. Yep.
Just a question on notation. In the book, it mentions differentiable, integrable, and continuous functions.
It does.
How do we notate that?
Ah.
For real value functions, do R and then the.
Okay, so I'm going to tell you that broadly, this class is not concerned with, so he's occasionally going to roll out the continuous functions or the differentiable functions as an object, but almost all of the book is focused on finite dimensional vector spaces, and those spaces are infinite dimensional. So the standard notation for that, just so you have it, so C01 is the standard notation for continuous functions on 01, continuous real valued functions. You might see R down here on 01, but this is actually appropriately the subject of like graduate level like functional analysis. And so it doesn't really show up in here. So when he does use this example, he always just writes it out. Cool. Okay. Yeah, the problem here is that this is an infinite dimensional vector space. And at some point here in chapter 1, he says infinite dimensional spaces are cool, but we're not going to study them at all for the rest of the book. Yep. These are the end of the vector space property. Yep. This is the vector space algebra properties. All of these properties are intended to make algebra run correctly. And what we're saying is, in the sort of way that mathematicians do, is that we start with the axioms and we can derive all the rest of the algebra from the axioms. Okay, so here's our big definition for the day. So are there any more questions about vector spaces before we go on to their properties? You guys are doing a good job of asking questions. I think that really get at the heart of the weirdness of this way of thinking about things. So we're going to do the first part of 1C, which is about subspaces. And it's going to be easier for me to give you the definition than show you examples of what I mean by that. So here's a definition. A subspace is a subset, of a vector space that is closed. Well, I should say, we should be more careful here. That satisfies 3 properties. One, it has a 0 element. So it's additive identity. Zero is in, let's call our subspace U. There's nothing fancy about that U, that's just to make sure that's capital. So whatever it is, 0 better live inside of it. 2, it's closed under addition. That means that U plus V should be inside of U for all U and V. So if I have 2 elements inside here and I add them, I can't leave. And if I have scalar multiplication, I can't leave by scalar multiplication either. 3. Closed. under scalar multiplication. That means that A U is in U for all A in field, all U in subset. Now, that might seem kind of mysterious, but the point of a subspace is a subspace is going to turn out to be also a vector space, a smaller vector space living inside of a bigger one. And so if you can show that these three properties hold, it turns out to be the case that these three properties are enough for U to be a vector space without having to prove all the axioms. You get it for free. So this is easier to understand what's going on, I think, if you just have some examples of what's happening. So you can have, for example, imagine you have this space. All right, what is that? If you're going to visualize that first as a shape, what is it? So this is inside of R3, which is a vector space. Plane. You in which plane?
The X and Y plane.
It's the XY plane, right? We're just saying set the Z coordinate equal to 0. Now, to assert that this is a subspace is to say 0 is inside of it. If I add two vectors inside of it, I can't leave. And if I stretch any vector inside of it, I can't leave. So I guess the idea here is that it's pretty easy to check that if you had two elements inside the space, that you get another one of the same form back again. This is in the space that you started in because it has 0 in the Z coordinate, right? You started with two things that had 0 in the Z coordinate. You end with something with 0 in the Z coordinate. So that's what you mean by closed under addition. You start with two objects in U. This is in U, this is in U, and you add them together, and the thing that comes out the other side has the same structure as the things you started with. Whatever it was you used to specify the subspace is still true of the result. Likewise, if you took some constant and you multiplied it by something in U, well, that's just going to be CX1, CX2, 0. Is that thing part of that set? Well, is it a real number, comma, a real number, comma, 0? Yeah, number, 0. So this was some scalar. This is in U, and this is also in U. So it's closed under addition. I start with two things in this plane, and I add them, and I get another thing in the plane out. I multiply something in the plane by a number, and I get another thing in the plane out the other side. The last condition was that? This is, yeah, this is over, yeah, I mean over R. And then the last condition is 0 in the set? Well, yeah, right, because you could pick, I mean, I'm allowed to pick any x1 and x2 I want. If I pick x1 is equal to 0 and x2 equals 0, this is also in U. And so it fits our definition of what it means to be a vector space. Okay. So vector spaces are, you can sort of think of them as being the analogy that most people carry around for vector spaces is they're like planes. You have some big space that's a vector space, and then you flatten it out. And as long as the plane that you make that flattens it out goes through 0, what you get out is sort of this restricted, smaller vector space that lived inside the bigger one. So the nice thing about vector spaces is the theorem, or subspaces, which is, I guess that was the theorem. Definition. What was a theorem? Jesus. Okay, so in your notes, where I wrote def, replace def with theorem. The theorem is, and this is my bad because my 3-year-old woke up 4 times in the middle of the night last night yelling about, I've never heard a 4-year-old at 4 o'clock in the morning yelling about wanting macaroni and cheese and donuts. That's if I feel seem a little off. Anyway, so the theorem is, I didn't even tell you what a subspace was, right? So, okay. So the theorem, did I tangle this completely? What did I say?
You said a subspace.
Did I say a subspace is a subset of vector space that is?
Subspace.
Okay, I completely mangled this. Okay, okay. So allow me to edit what I said slightly to fix this, okay? And you have my apologies for this. So better to admit error than to BS my way through it. Okay, so the definition is that U is a subspace of V if U is a subset of V that is a vector space. So that will hopefully make things more clear. A subspace is a subset that is a vector space in its own right, like what we just did right here, right? It's a vector space. It follows all the vector space rules. Okay? A subspace is a subset that is also a vector space. Now, the properties they wrote down are actually the theorem. The pretty amusing tank job right there. What the theorem says, the theorem is supposed to give you a way of checking to see that something was a vector space. If I want to know something is a vector space, technically I have to check all of those vector space properties: commutativity, additive identity, the zero being in there, associativity, all the rest of it. I don't want to have to do that every single time. And so what the theorem says is that U is a subspace of V is a subset, and property 1, 0 is in U, property 2, U plus V is in U whenever U and V are in U, and property 3, lambda U is in U for all lambda in the field and U in U. I'm sorry for destroying your notebooks. Anyway. Okay. So subspaces are cool. And one reason subspaces are cool is because they give you lots of examples of vector spaces. As soon as you have a vector space, any closed subset turns out to be a vector space. And there's some awesome ones. Some incredibly useful ones. In fact, I'm curious, if I just told you R2, here we go, there's R2, regular old Euclidean space. What are the subspaces of R2? What are the things, the sets that you could draw in here that contain 0, are closed under addition, and are closed under scalar multiplication? Every line. That passes through, got to pass through the origin or 0 won't be in it, right? So any line that you draw in R2, if you imagine vectors living inside here, if you added 2 vectors living in a line, you stay in the line, you can't leave. And if you start with a vector V in the line and you multiply it by C, well, you can stretch this way, or you can turn around and stretch that way, but you're not going to leave the line, right? Any others? Okay, so lines through 0, 0. So there's one pile of subspaces, right? Anything that looks like this is going to be closed under addition and closed under scalar multiplication and contains 0. If 0 is not on the line, you get this special object called an affine line, but they're an affine subspace, but those which can be studied, but not for our definition. It's important 0 is in there. Okay. Any others? Yep. 0.0. Okay, 2 simultaneous answers there. That's right. Remember, we talked about the vector space consisting of just the point 0 as a vector space. So just the point all by itself, 0, 0, is a subspace. It's the tiniest vector space living inside of R2. Any others? Yep. R2 itself is a subspace, right? So we're not in a position yet where we can prove that these are all the subspaces of R2, but this completely characterizes the linear subspaces of R2. What about R3? What do I have to add to the picture in R3? What was that?
So a lot of planes.
Planes, right? But the planes have to satisfy, or the basic idea with planes is that the same closure properties apply, right? If you have two vectors living in the same flat space and you add them, you have no way to get out of the plane that you're in, right? If you're in a flat plane and you get added to another vector in the same plane, you can't leave. Planes are closed under addition. Planes are also closed under scalar multiplication, because if you're living in a plane and you get multiplied by a scalar, you get longer, but you don't leave the plane, right? You can't suddenly get a z coordinate. What about the zero condition? Same thing. So we get a trivial subspace, we get lines through the origin, we get planes through the origin, and we get all of R3. Okay, in all of these cases, the point of writing this stuff out is what I'm trying to emphasize here is that you should think of linear subspaces and vector spaces as being flat in some way. The combinations we're making are linear. We're never squaring anything, and we're not multiplying anything. So the vectors never get multiplied in a way where anything can curve, right? Everything is being added like a vector, which means it's flat addition. Okay, so linear algebra is the study of flat spaces like this. Okay, now there's some way more interesting ones in R2 and R3. So here's one of my favorite examples. Okay, so we talked before about this guy, right? So I'm gonna write a symbol down. What does that mean? C to the C. Right, F, it takes complex numbers into the complex numbers. That's a lot of them. All the F's that look, I made a lot of complex numbers, right? A lot of ways of assigning the entire set of complex numbers to the other entire set of complex numbers. But living inside that is a really special family of functions. So functions with absolutely convergent power series. So you pretty much everyone in here, even if you haven't taken complex analysis before, you've seen a Taylor series, Taylor expansion, right? Like a power series in the context of Taylor series. So it turns out if you take two functions that have absolutely convergent power series, the resulting power series also converges absolutely. Just a fact, right? The limit still exists. So if you have absolutely convergent series and you add them, you get another one. And if you multiply an absolutely convergent series by a number, well, it started out absolutely convergent. It's going to remain absolutely convergent after you multiply it by a number. And 0 certainly has an absolutely convergent power series. It's just a bunch of zeros in a pile, right? So it turns out to be the case that this super nice set of functions is a subspace of this really nasty one under the same operation, okay? And this is where the connections between linear algebra and calculus begins, that a lot of things in calculus can be thought of as vectors in this way. Okay. So in your higher classes that come out of here, the language that we're going to be building here, mostly in finite dimensions, generalizes really nicely to situations like this. If you want to think about how could that possibly be a vector, well, just imagine if I just told you the coefficients, you could tell me the power series. And that's basically like a sequence of numbers, which you can think of as being a vector. Okay. So here's a typical exercise having to do with subspaces. So prove that I'll give you an easy one first, right? So prove that x1, 2x1 plus 3x2, x1 plus 1. Not a subspace. There's two different ways of seeing that this is not a, what that factor is. Okay, so what I'm doing is I'm taking every possible real number x1 and x2, I'm putting it into this form, and I'm looking at the set of everything that comes out the other side. So, e.g., if you picked x1 equal to 1 and x2 equal to 1, the element you would get out would be 5, 1, 2. And if you put x1 is equal to 1 and x2 is equal to 3, you would get out the element 11, 1, 2. So this is the sort of things that are generated by a rule like this. So how would you go about showing that's not a subspace? I can think of at least two ways to do it. Yep. That's the easiest, always the very easiest thing to do is to check if 0 is in the subspace or not. 0 can't be in here because you're never going to be able to get rid of this 1, right? There's no way to get the 1 out of here. And actually, this is 0 in here. Yeah, no, it's not. Because as soon as you try to cancel the 1 out, you're going to end up with another coefficient here, right? Another way to do it is this closed under addition? Well, if you add two of them together, there's going to be this +1 and another +1 coming out the other side. So you won't even retain the form of the original rule, right? So this space is not even closed under addition. So normally when you're asked to show something's not a subspace, it fails because 0 is not in the set. 0 not in the set. And if 0 is not in the set, it is not a subspace. Easiest possible check to see if something is not a subspace. Now, 0 being in there would not force it to be a subspace, but it certainly would tell you that it's not one. On the other hand, you might get asked to show something like, show 2a plus 3b ab, where a and b are real. So that's a subspace.
So when you say like it has to, after like condition has to be in that form, that means you could like just like mess with like the new vector to get it into that vector.
That's how it's going to work. Yeah. So what's going to happen is you're going to have to do an addition and then rewrite it so that it's in the correct form when you're finished. Is the way that it tends to go. Yep.
0 is unique.
Yes. 0 is unique. Yep. Oh, and a linear combination setup like this. Yeah, for sure. Yep.
For this last slide, what are you plugging into x1 and x2 to show that it's not?
I mean, if you just took two random, I wouldn't plug anything in at all. What I would say is I would start by doing this. I would write 2a plus 3b, a plus 1. And then I would add that to 2c plus 3d, c plus 1. And if I took those two elements and I add them together, so what's supposed to happen is whatever's in this slot is supposed to be here as well, but with a +1 stuck to it, right? Whatever number is here should also be here, but with a +1. If you took these two things and you added them together, so I picked arbitrary elements, not numbers, but arbitrary elements. And if I add these together, what you end up with is 2a plus c, and then 3b plus d, comma, a plus c, comma, a plus c plus 2. I started with something where I had a number and then that same number +1, but you get the failure of closure under addition because this number and this number now differ by 2 instead of 1. So you've left the set that you set up. Yep.
So if there's no one there with that.
Yes, actually, it would be. If you erase the 1 here, this turns out to be a subspace, right? Like linear things that are built out of linear combinations are always going to turn out to be subspaces, as long as the linear combinations don't involve scalars. It's like this extra thing. I mean, what this does is it pushes it away from 0, and that forces the addition to fail to be closed. Yep.
I still don't understand why it does not close under additions.
Every element in this space
Mhm.
has the property that whatever is here and whatever is here have the relationship that this number and that number differ by +1, right? That's the rule I use to set the space up. Every single thing in this set has the property. If you put a 2 here, there'd be a 3 here. If you put a 5 here, there'd be a 6 here. If you put an 8 here, there'd be a 9 here. Now I've taken 2 of these elements and I've added them together. What if I put a 10 here for A plus C? What would be here? 12. They don't differ by 1. So it fails the rule that says whatever's here is supposed to be 1 more than this. So this is not closed. I mean, this doesn't have the right structure. This is not closed because this number and this number differ by 2, not by 1.
Does it mean these 2 points or these 2 planes are not the same or something like that?
Which 2 points?
I mean, like, these are
Those are points.
points. So the point they don't live in the same plane or on the same line. Is that what it means?
No, geometrically what it means is that the plane doesn't pass through the origin. You're trying to add 2 points together, but the plane they live in doesn't pass through the origin. And so the sum of the 2 points doesn't live in the plane that they both sit inside of. This looks like a plane,
Mhm.
but if you add the vectors in that plane together, you don't stay inside the plane because you're adding points. And I mean, there's geometry running around in the background. I don't really have the ability to say much more about this other than the fact that you start with this, you pick a point here and a point here, that's these 2 points, P and Q, and you added them together and you ended up here somewhere. This is P, this is Q, and you end up here at P plus Q. We don't want that. We end up outside the plane because the structure is not correct.
Okay, that makes sense. Thank you.
Okay, on the other hand, if you're here, you are a subspace because you can do the same game where you take the arbitrary points and you add them together and you can resort them so they have the same form. If you took 2a prime plus 3b prime plus or comma a comma b, and you added that to 2a plus 3b comma ab, well, you get 2 times a plus a prime plus 3 times b plus b prime, comma a plus a prime, comma b plus b prime. And if you don't see that that follows the same rule, that this lives in this set, you could make the substitution if you like, s is equal to a plus a prime and t is equal to b plus b prime. And what you're going to get is 2s plus 3t st. And that has the same form that this does. So we add 2 arbitrary elements, we end up back where we started. Yep.
Oh, when writing proofs, is that last step necessary?
It is not necessary. It's a clarifying step if you get to something where you're trying to show that it's true. Because I would say from right here, I've shown that there are real numbers. So it's 2 times a number plus 3 times a number, and then that number and that number in those positions. For me, that would be enough to say it's in the right set. If it's not obvious to you that it's in the right set, you can do the substitution and make it clear that it's got the right form. But this form and that form are the same form. To make sure that you don't need to say that if you don't want. Yeah, if you've restricted yourself to the real numbers and the real numbers is your scalar field, you don't need to. It's lurking in the background and it won't cost you to say that, but you don't need to if you don't want to. Anything else? Yep. That's right. There's examples that violate each property, but not the others. In fact, that's an exercise that may come up in the homework, or it would be write me down a set that's closed under addition but fails scalar multiplication. Right? That's actually pretty easy to do because half lines you can imagine if you have a vector, not a line, but array, any two vectors in an array, if you add them together, stay inside the array. If I have a vector v and I have a vector w and they're parallel to each other and I add them, I stay in the same array. And 0 is in here too if I put this at the origin. The problem is that if I multiply this by a negative scalar, I leave the space. So that's an example of scalar multiplication failing, but all other properties hold it. Anything else? Okay. So I don't know if you guys could tell, but this is simultaneously, so what's the challenge of linear algebra? It's already started to show up in what we've done here, right? Is that this combination of really abstract ideas like the definition of subspaces and these proofs involving these abstract symbols, and then these weird concrete examples where you have to exhibit that the properties hold, right? But this is the way this is going to be, is an interplay between abstract theory where we set up this machinery about vector spaces and subspaces, and we prove arithmetic, sort of big theorems about how they work. And then there's going to be these concrete applications where we're going to be looking at stuff like this as well. Okay. Yeah, so I think that the best thing you could do, I guess we don't have, is it Wednesday? Okay, so we don't have class tomorrow, which is unfortunate because I'd love to meet you guys again. I'm not going to begrudge you your holiday, but your Tuesday, Friday. Yeah, so what you should try to do is you should try to read ahead into the second part of section 1.c is way more abstract than kind of what we've done so far. It talks about how you take subspaces and add them together to make new subspaces. So the idea of orthogonality is going to show up and direct sums, and it's going to seem more abstract and stranger than some of the stuff we've done so far. So you should read ahead if you can before next time. All right. So the homework that's posted, you guys are well equipped to attack, and please be on Slack. I'm gonna have office hours on Friday, and I'll see you there hopefully.
What time are your office hours?
I'm gonna have